Hey everyone, let's learn how to tackle this educator problem, necessary family reunions. So this is a bit of an interesting problem. The problem statement gives us an array of ones and zeros, and these ones and zeros represent a direct family relationship between the number in the row and the number in the column. So for instance, I actually like the second test case quite a bit. Um, this one here represents that number one and number two, say, right? This zero index and this one index have a direct relation, right? So if we can imagine there's like three people here, right? Um, you know, one, two, and three. And each of these rows in these columns will represent one of these people. So this one indicates that one and two are related, right? This one here represents that three and two are related. And the ones on the columns, obviously, or on the diagonal, obviously don't mean anything. And you can actually see that it's mirrored over this diagonal. So these ones here are redundant. But essentially what's happening here is that one and two related and two and three are related. So essentially, they're all one big family, right? One and three are indirectly related family members. And so when you throw family reunions, you only need to throw one for all three of those, hence the output one. Great circling. So there's a way to solve this using like a BFS or a DFS. We're basically, you have a bunch of, say we have, five people, and they're all in their nodes, one, two, three, four, five. And based on the connections, let's say, like we said, one and two are connected, and then two or three and three are connected. And then let's say there's also four and five, a connection between four and five. And you can run uh, like a DFS on each of the nodes. And when you encounter a node with a DFS, you essentially mark it off with a number. So like this is DFS number one, right? Keep DFSing. All right, DFS number one is ended. Let's go to the next number. Okay, these are all done. Let's start here with DFS two. And then you're done. And now all of the nodes have been visited and you've gone through two groups total, and you've grouped them all together. So that's probably the easiest way to do this, but we're actually going to be, as requested by the problem statement, taking a little bit of a different approach. We're going to be using the disjoint set or the union find, aptly named, data structure. So, let's step away from graphs and kind of just talk about this problem in general. So let's say we have three people, one, two, and three. Now, if I just wanted to like update this array, right? If I wanted to say, all right, two and three, you're related. Maybe you could be like, okay, so maybe I'll have this array, and this array will store, you know, the people we see that they're related to. So if two and three are related, I'll just erase this three and put a two in this third position instead, because three is related to two, so we can effectively just say, okay, two is three's family member. But then what if I then say, all right, now one and three are related, right? Then I have to look here and maybe I'll say, again, update this bigger number. I'll say, okay, cool. Now one is three's family member. But you can see that doesn't preserve any data. If I then look at like these two nodes, even though two and three are related and one and three are related, these two should all be related, but that's just not the case, right? You can see they have completely different data in there. Three has not given them anything. So what we instead do is we use a sort of tree-like data structure to represent these relationships. So like this one, two, and three, we can actually think of it as three different nodes, right? And each node, we can just store one value for them. And that's the root of the tree, of their family tree, I guess you can think of it. And the actual who's at the root of the tree is pretty arbitrary. But the important thing is that all operations must be done with respect to that root. So every time you're adding someone to that family, they need to know who the root of the tree is because everyone else in that family is underneath that same root. So if I just show you, we start off, 1, 2, and 3. 3 people, they're each their own separate tree, right? They're separate families. If I then union 2 and 3, what happens there is we still have 1 by itself. And then what we do is we have these 2 trees, right? The 2 tree and the 3 tree. We put one of the trees underneath one of the other as a child of one of the other. Let's just say we'll put the 3 underneath the 2 because 2 is less than 3. At this point, these 2 have been, physically grouped together. And the strength in this approach is now let's say I want to, group 1 and 3 together, right? What I can do, again, let's keep the algorithm of putting the smallest number or the bigger root under the smaller root. What I can do here is I know 3's parent, right? Effectively what it would be storing, the root of its tree is this 2. And the root of this 1 tree is just the 1. And remember, all of these nodes in this 2 tree represent nodes that are in one family. So you could have like, a 4 here and like a 5, and this 5 could be attached to a 6. The important thing is they all have parent 2, which means they're all in that 2 family. So what we'll do here is if we're unioning that with 1, again, we'll say bigger under smaller just for purposes of drawing it out. We can put all of that under that 1. So we now say 2's parent is now 1. And so if at any point you go to find the parent of 3, how do you do that? Well, you look, 2 is 3's parent, but then you look at 2's parent. 2's parent is 1. And so 3 is under the 1 tree. And so that's kind of inherently how the structure is defined. It's trees representing groups of families, where each node stores their parent. And if we keep going up the tree, we eventually get to the root, which is a representation of the family as a whole that we can use to do the operations on. It's not super duper intuitive. I'll like give in. I think how it solves the problem, you can see how it solves the problem, but like by itself, you're like, man, I would not have, you're likely thinking I would not have thought of that as a way to represent this problem. But that's okay. I think when you actually like implement it, you can kind of start to see how it helps and what other situations it might help in. So let's start with find. So as I said, each of these nodes will store their parents. That's what this vector is here. And that's actually what we're doing here with this initialized set. This initialized set, it'll make a vector, say n is, 3. This is 0 indexed, unlike the 1 indexed examples we've been doing. But essentially, this stores 0's parent, this stores 1 parent, and this stores 2's parent. Initially, all the parents of the nodes are themselves because like I said, we start off with just like independent nodes, right? Each node is in its own family and thus in its own tree. So this kind of represents it. When a node's at the top of a tree, it's its own parent, right? That means it doesn't have a parent. So what we want to do is we want to find the ultimate parent of this int x. And what that means is really the family it's a part of. Because just like this 3, right? Its immediate parent is 2. Let's forget about this whole 1 debacle here. And remember when they were all under the family of 2. 3's immediate parent is 2. That's good. It's in the 2 family. But 6, its immediate parent is 5. So if we really want to know that it's in the 2's family, we got to say, okay, 6, what's its parent? It's 5. Okay, what's 5's parent? Oh, it's 2. What's 2's parent? It's itself. So when we hit a node that is itself, we know we're at the root of the tree. There's no way further up to go. And therefore, we've reached the kind of representative of that tree. Coding this, very straightforward. All we're going to do is we're going to say if x is equal to parents x, effectively if x is its own parent, then we would just return it because it is the ultimate parent. And if that's not the case, then parents x, we want to go, again, recursively up that tree. So we have that new parent. We want to find that parent's parent until we get to a parent that doesn't have its own parent, doesn't have a new parent. So this will return find of parents x. Effectively saying, like in that example with, in that example with 6, 5, and 2, parents of 6 would be 5. So you'd be then recursively calling find on 5, which would get 2. And this would trigger this base case where it would return 2. And so this would return 2. So this would return true, 2, its ultimate parent. So now let's talk about union. So like I said, union represents the grouping of trees together, right? If we had this one tree here and we had, a 2 tree with children 3 and 4, we're grouping the families together. Now, remember how the trees themselves are structured, right? 4 points upward, right? We store parents. So 4's parent is 2, 3's parent is 2. 2 is looping back on itself. So is 1. They do not have really a parent right now. So if we were to just pass in, say, union 1, 4. So say we were to union 1, 4. The naive thing to do is maybe to say, okay, I'll update 4's parent and make it 1. But now what you've ended up with is you have ended up with 3 pointing to 2 and 4 pointing to 1. But what you should see is that you've had a node in the 2 family and you've had a node in the 1 family and you've combined them. So now everything should be in 1 family, but that's not what you see here. They're actually in 2 separate trees, 2 separate families. So that's not what we want. Now, you're inherently losing some data. You're destroying it because 4 already has a parent pointer and you're overriding that. Now, if only there was a representative of that family that didn't point anywhere meaningful. It's the root. So what we do is we first call on the nodes we're trying to union, we find the parents by calling find on them. If we call find on 4, we get 2. And then we can update one of these parents to point to one of the other parents. Here we're not losing any data, right? This 2 wasn't pointing anywhere. It was it was kind of the root of that 2 tree. And then by moving that 2 tree underneath the 1, so right now we have 2 pointing to 1, and then 3 and 4 pointing to 2. Now running find on 4 will return 1, and running find on 3 will return 1. So they're now effectively all under the 1 root as well. And so that's the intuition here behind, we can just say update A to be find A set and update B to be find B set. And you should see now, like I said, this will initially store all of the values by themselves. And so we'll just have, this is just acting as the parents array. And then here we'll just say that, parents or set of effectively updating the parent. It doesn't matter which we do here. You can say set of A equals set of B. We'll talk about that later, but it doesn't matter which way we really do it. We're putting one root under the other. It doesn't matter if we put 2 under the 1 or 1 under the 2. They'll both work. Alrighty. So now for the actual NFR bit here. So, first thing, we want to run this initialize set so we can actually do our union find operations. So let's do that. This is actually a vector event. I'm not sure why it's called set, but since it is, I'll call it set. Equals initialize set. So it should be spelled correctly, maybe. we'll pass in p dot size. This is how many slots we want in a vector. And then what we'll do is we'll iterate over our p array. Like so. Just go y is equal to 0, y is less than p dot size, y plus plus. And we'll call union. Pass in the set, and we'll union x and y. But remember, we only want to do this when there's a 1. So we can actually just do that by saying if e x y, because 1's evaluate to true and 0's evaluate to false. So if while iterating, we iterate through all the squares on the grid. If there's a 1, we call union on itself. Remember that calling union on like something itself, it's not going to do anything. But again, we'll fix that later. So here we see this 1. We'll call union on like 0 and then 1. That's good. So now we've applied all the unions, and we should hopefully have extracted these parental trees, right? We have our final families built into trees. There you go. What I'll do is I'll use an unordered set so we don't have duplicates. And we'll have these store the families. Now remember, when we're talking about storing families, what we really care about are the roots of the trees. If I were to say, just iterate through, like this set here, and say like, res dot insert set x. Remember, set stores the parent. So like here, even though they're all in one family, you'd be storing like a 2 here, a 2 here, and a 1 here, and a 1 here. Because remember, root loops back to itself. So you'd actually have 1, 1, 2, 2, which is sort of implying there's 2 distinct families. That's not what we want. What we really want is we want to know the root of each tree that each node is contained in. So 3 is contained in family 1, 2 is contained in family 1, 4 is contained in family 1. And again, hopefully this should be clear, is just a find operation, right? Find that representative that is shared across all nodes in that tree. Find set x, set extra parentheses. There we go. And then return the rest. Is there anything I have forgotten about? Maybe. Let's run the code and see if it works. We need to import ordered set. Res dot size, because remember, everything in the res is unique, so this is just the number of parents in there. Okay. We can see we do get 1 here. There's a few things I wanted to discuss before submission. Hopefully I remember them all. One is that you see these iterations. Remember how I said at the very start that this array is actually it's mirrored along its diagonal. Effectively, this term is saying that 0 and 1 are related, and this one's saying that 1 and 0 are related. Once we union, they'll like both be in one tree anyways, so it doesn't make sense to union them twice. So what we can just do is we can just like replace this with x so that we're only ever iterating along, like we're only ever actually checking like these parts of the array. We don't need the diagonal because that just maps 0 with 0 or something like that. Another thing is currently the time complexity of this find operation is O of n, right? We're tracing all the way back up the tree. But using some tricks, we can actually get this all the way down to O of effectively 1, almost constant time. One of them is very simple. I'll write it up real quick. It's basically just doing this. So every time we run find on a value, so remember, let's pull up the example from earlier. We had 3, 4 connected to 2, which is connected to 1. will actually assign that root value as the direct parent of a certain value. So for example, this 4, find of parent x, right? It'll run the find on 2, which will return 1, the ultimate root of the tree. It'll actually just straight up be like, okay, I'll then assign that 4's parent to be the 1, right? And so this, I think it's called like path compression, effectively putting all the values at the end of the day that are under a tree at the directly underneath the root, so they only ever need to make one jump. They actually don't need to make successive recursive calls. The other one I think has to do with merging trees. So if you have like two big trees, big family trees, you actually it's about the order of merging. I think you generally want to merge bigger trees underneath smaller trees or something like that. Just based on the number of nodes that are in the tree. And with both of those optimizations, you end up getting effectively constant time. The rank approach you do to optimize unions, you do need to have a separate array to store the ranks of each chunk. So here, like the rank of the 1 family. So I'm not going to implement that right now. But keep in mind, maybe if you're doing something where time complexity is really necessary, I'd recommend looking into it. But regardless, with those optimizations, shouldn't matter here. Hopefully I didn't make it fail. Yeah, you can see it works. And that is all. Hopefully that helped out. I don't think this is something you really see otherwise, although I think we're teaching it next semester, so maybe not. But I think it's a cool little construct to use in different problems. So with that being said, thanks for watching. I'll see you in the next one.